What if everything you thought you knew about heat was wrong? Imagine drifting in space closer and closer to the sun. Not from the safety of Earth, not through a telescope, but they're suspended in the emptiness. The sun fills your vision, an overwhelming sphere of blinding light, its surface boiling at around 5,500 degrees Celsius. Above it, the corona stretches outward, reaching temperatures of millions of degrees. According to NASA, this outer atmosphere is paradoxically hotter than the surface itself. You would expect something obvious to happen. You would expect to feel the heat, but you wouldn't. Not in the way you think, because here is the contradiction. The closer you get to the sun, the more intense the radiation becomes. Instruments begin to register extreme energy levels. Photons stream past you in unimaginable quantities. Solar particles race outward at high speed. Everything suggests overwhelming heat, and yet the space around you remains almost completely cold. Not just cool, not just manageable, but fundamentally deeply cold in a way that seems to defy everything you have ever experienced. This is not a thought experiment pulled from science fiction. It is something scientists have had to confront directly. Spacecraft like the Parker Solar Probe have travelled closer to the sun than anything before. According to NASA, it has passed through regions where temperatures of the surrounding plasma reach over 1,000,000 degrees Celsius. And still the spacecraft itself does not melt into nothing. Instead, it survives. It carries a heat shield carefully engineered facing the sun. Behind that shield, its instruments operate at near room temperature. The probe is flying through an environment that is in one sense unimaginably hot, and in another sense almost empty of heat. That should not be possible, because on Earth heat behaves in a way that feels intuitive. Stand near a fire and you feel warmth spreading through the air. Step closer and the heat becomes more intense. The air carries that heat to your skin. Molecules collide, energy transfers, and your body reacts instantly. Heat spreads, heat fills space. That is what we expect. But space does not behave like air. It does not behave like anything we are familiar with. And this is where the contradiction begins to deepen. Because when scientists talk about temperature in space, they are not always talking about what you would feel. They're talking about something more elemental, something that challenges the very definition of heat itself. In laboratory terms, temperature is a measure of how fast particles are moving. The faster they move, the higher the temperature. In the sun's corona, particles are moving incredibly fast. That is why the temperature is measured in the millions of degrees. But there is another factor. How many particles are there? In the corona, despite its extreme temperature, the density is incredibly low. There are very few particles in any given volume. That means that even though each particle carries a huge amount of energy, there simply are not enough of them to transfer that energy efficiently. So when you drift through this region, very few particles actually collide with you. Very little energy is transferred to your body, and that changes everything. Because what you feel as heat is not just energy existing around you, it is energy being transferred to you. Without that transfer, the sensation of heat disappears. This is the heart of the paradox. The sun is constantly releasing enormous amounts of energy. According to NASA, it emits about 3.8 times 10 to the 26th power watts of power. That energy spreads out in all directions, travelling through space as radiation. And yet the vast majority of space remains at a temperature close to minus 270 degrees Celsius. Almost absolute zero. How can both of these things be true at the same time? How can the most powerful source of heat in our solar system fail to warm the space around it? At first glance, it feels like a contradiction, a flaw in our understanding, a missing piece that should not exist. For centuries, humans assumed that heat worked in a simple way, that it spread outward, filling the surrounding environment. That proximity to a heat source automatically meant higher temperature. But space is not an environment in the way we are used to. It is not filled with air. It is not filled with matter. It is for the most part empty. And emptiness behaves differently. This realization did not come all at once. It emerged slowly through observations, experiments and missions that pushed further into space than ever before. scientists began to notice patterns that did not match their expectations, temperatures that seemed too low, regions that should have been warm but were not. The deeper they looked, the stranger it became. Because the problem is not just that space is cold. The problem is that our intuition about heat is built on an environment that barely exists beyond Earth. On our planet, heat transfer happens in three main ways: conduction, convection, and radiation. Conduction requires direct contact. Convection requires a fluid like air or water to carry heat. Radiation can travel through empty space. But only one of these works in the vacuum of space, only radiation, and radiation does not behave like the other two. It does not fill space with warmth in the same way. It travels in straight lines. It passes through emptiness without interacting unless it encounters something with mass, something that can absorb it. Without that interaction, the energy simply continues on its path, unfelt, unnoticed. And that leads to a question that seems simple but is anything but. If the sun cannot heat empty space, then what exactly is heat? Is it energy? Is it motion? Is it interaction? Or is it something that only exists when matter is present to experience it? This question has forced scientists to rethink one of the most fundamental concepts in physics. Not just how heat moves, but what it actually is. Because the truth is, the sun is not failing to heat space. It is doing exactly what physics allows it to do. The real issue lies in how we define heat in the first place. And once you begin to separate energy from sensation, something shifts in your understanding. The universe starts to feel different, colder, stranger, less intuitive, because the warmth you feel on Earth is not a universal rule. It is a special case. A result of being surrounded by matter. Take that matter away and the rules change completely. And this is where the mystery deepens. Because if space itself cannot be heated in the way we expect, then how do planets like Earth become warm enough to support life? Why does sunlight feel hot on your skin? Why does standing in direct sunlight raise your temperature, even though the space between you and the sun is almost perfectly cold? There is a missing step in the story. A crucial interaction that transforms invisible radiation into tangible heat. And until you understand that step, the paradox remains unsolved. Because the sun is not what it seems, and neither is heat. The mystery begins with something so ordinary you almost overlook it. Sunlight. Every day it travels across 150 million kilometers of space from the sun to your skin. It lights your world, warms your surroundings, drives weather, fuels life. It feels immediate, direct, and obvious. You step into sunlight and you feel warmth. You step into shade and that warmth fades. It feels simple, but hidden inside that simple experience is a question that has quietly unsettled scientists for decades. If the sun's energy travels through space to reach you, then why is the space in between still so cold? Because it is not just cold, it is unimaginably cold. According to the measurements of the cosmic microwave background, the average temperature of the universe sits at about 2.7 Kelvin. That is just a few degrees above absolute zero. Even within our own solar system, far from planetary atmospheres, space itself does not retain heat. This creates a strange contrast. On one hand, you have the sun radiating enormous amounts of energy. On the other, you have a universe that remains frozen, almost untouched by that energy. It's like standing beside a roaring fire, but the air around it refuses to warm. At first, scientists assumed this was simply a matter of distance. The further you go from the sun, the more its energy spreads out, becoming weaker. That part is true. Energy does dilute over distance. But this explanation does not solve the entire problem, because even relatively close to the sun, space itself does not behave as expected. When spacecraft travel through the inner solar system, they are surrounded by intense radiation. Instruments detect high-energy photons, streams of charged particles, and solar wind moving at incredible speeds. Yet the vacuum around them does not become warm in the way air would. This is where the mystery sharpens, because something is clearly moving through space. Energy is there, it is measurable, it is real, and yet the space itself does not seem to absorb it. It does not heat up. To understand why scientists began to look more closely at what we actually mean when we say something is hot. On Earth, temperature is something you feel through interaction. air molecules collide with your skin, transferring energy. The faster those molecules move, the more energy they transfer and the warmer you feel. But in space, there are almost no molecules. There is no air to carry heat. There is no medium to distribute energy evenly. Instead, there is mostly emptiness. So the question changes. It's no longer about how much energy is present. It becomes about how that energy interacts with matter. And in space, interaction is rare. This idea began to take shape through decades of observation. Telescopes like the Hubble Space Telescope allowed scientists to study distant regions of space, measuring temperatures in nebulae, interstellar clouds, and the vast emptiness between stars. What they found was consistent. Regions with more matter, even very small amounts, showed measurable temperatures. Regions with almost no matter remained extremely cold regardless of how much radiation passed through them. This pattern pointed to something fundamental. Temperature is not just about energy existing in a location. It is about energy being shared between particles. Without particles, there is nothing to share, nothing to collide, nothing to transfer energy. So even though radiation passes through space continuously, it does not raise the temperature of the vacuum itself. It simply moves through. This realization forced scientists to rethink a basic assumption. Heat is not something that fills space. It is something that emerges from interaction. And that leads to an even deeper question. If space does not hold heat, then what exactly is sunlight doing as it travels? Because sunlight is not nothing. It carries energy. It carries energy. It exerts pressure. It can even push spacecraft using solar sails. According to NASA, photons from sunlight carry momentum, and when they strike a surface, they transfer that momentum. This is how solar radiation pressure works. So clearly, sunlight is not just passing through space without effect. It has the ability to interact, but only when it encounters something, a surface, a particle, a molecule. That is when the transformation happens. That is when energy becomes heat, and this is where the mystery becomes more subtle. Because from your perspective on Earth, it feels like sunlight itself is warm. But what you are actually experiencing is not the warmth of space. You're experiencing the interaction between radiation and matter. Your skin absorbs photons. Those photons transfer energy to the molecules in your skin. Those molecules begin to move faster, and that motion is what you feel as heat. So the warmth is not in the space between you and the sun. It is in the moment of contact. The moment and energy becomes motion. This distinction may seem small, but it changes everything. Because it means that heat as you understand it does not exist in empty space. It only exists where matter is present, where interaction can occur. And this explains something that once seemed impossible. Why astronauts in orbit can experience extreme conditions depending on whether they are in sunlight or shadow. In direct sunlight, their suits absorb radiation and heat up. In shadow with no incoming radiation and no surrounding air, they can become extremely cold. The environment around them does not hold heat. It does not buffer temperature. It does not behave like air or water. It simply allows energy to pass through. This creates sharp contrasts, sharp boundaries between hot and cold, sharp differences that would not exist on Earth. And it reveals something profound about the nature of the universe. The warmth we experience is not a property of space. It's a property of matter interacting with energy. Take away the matter and the warmth disappears. Even if the energy remains, this realization did not come easily. It required a shift in perspective, a willingness to question assumptions that felt obvious. For centuries, heat was treated as something that could be stored, transferred, and distributed in a medium. But space is not a medium. It is, for the most part, the absence of one. And that absence changes the rules. It forces us to separate concepts that we usually combine. Energy and heat, presence and interaction, radiation and temperature. Once you begin to separate them, the paradox starts to resolve. The sun is not failing to heat space. Space simply cannot hold that heat. It has nothing to hold it with. But this raises an even more intriguing question. If heat only exists through interaction with matter, then how does something as vast as a planet become warm? How does Earth, surrounded by cold vacuum, maintain temperatures that allow oceans to exist, weather to form, and life to thrive? Because clearly something is capturing that energy. Something is transforming it. And that process is far more complex than it first appears. because not all matter behaves the same way. Not all surfaces absorb energy equally. Not all environments respond in predictable ways. And somewhere in that complexity lies the next layer of this mystery. Because understanding why space stays cold is only the beginning. Understanding how anything becomes warm at all is where the real story unfolds. For most of human history, the behavior of heat seemed so obvious that no one questioned it. Stand near a fire and you feel warm. Step away and the warmth fades. Heat radiates outward, filling the surrounding air, spreading from hotter regions to colder ones. This pattern was so consistent, so deeply tied to everyday experience that it became a foundation for how we understood the physical world. Long before modern physics, ancient thinkers imagined heat as something almost tangible, something that flowed, something that could move from one object to another like a fluid. By the time of early modern science, this idea took on a more formal shape through what was known as the caloric theory. Heat, according to this theory, was a kind of invisible substance, a weightless fluid that could be transferred between bodies. When something heated up, it was because it contained more of this fluid. When it cooled down, it lost it. At first, this seemed to work. It explained why hot objects cooled over time. It explained why heat moved from warmer regions to cooler ones. It even helped scientists develop early thermodynamic ideas. For a while it was enough, but like many early models, it carried hidden assumptions. It assumed that heat behaved the same way everywhere. It assumed that the environment through which heat moved did not fundamentally change the process. And most importantly, it assumed that space itself was something that could hold and transmit heat in the same way air or water could. That assumption would later prove to be deeply misleading. As science advanced, particularly during the 18th and 19th centuries, cracks began to appear in the caloric theory. Experiments started to show that heat was not a substance but a form of energy. Count Benjamin Thompson observed that boring cannons could produce seemingly endless heat through friction, suggesting that heat was generated by motion not released from a stored fluid. Later scientists like James Clerk Maxwell and Ludwig Boltzmann developed the kinetic theory of gases. They showed that temperature was related to the motion of particles. The faster particles moved, the higher the temperature. This was a major shift. Heat was no longer something that flowed like a liquid. It was something that emerged from motion, from collisions, from interactions between particles. But even as this new understanding took hold, one key assumption remained largely unchallenged. That heat in some form could still spread through space itself. Because on Earth, that is exactly what it appears to do. When you light a fire, the air around it warms up. Convection currents carry heat upward. Warm air rises, cool air sinks, and the entire room gradually becomes warmer. Even without direct contact, you can feel the warmth spreading. It feels like heat is filling the space. And in a sense it is, but only because that space is not empty. It is filled with air. Air that can move. Air that can carry energy. Air that can collide with your skin and transfer that energy to you. Remove the air and something strange happens. This was demonstrated dramatically in vacuum experiments. When scientists placed objects in a vacuum chamber and removed the air, the behavior of heat changed. Convection disappeared. Conduction was limited. Only radiation remained. Objects no longer warmed their surroundings in the same way. They could glow. They could emit energy. But that energy did not accumulate in the empty space around them. It simply passed through. This was one of the first hints that space might behave very differently from the environments we're used to. But it was not until the space age that this idea became impossible to ignore. As rockets began to leave Earth and instruments were sent beyond the atmosphere, scientists gained access to a completely new kind of environment. One where air did not exist. One where the assumptions built from everyday experience no longer applied. Early missions revealed something surprising. Satellites in orbit did not experience gradual warming from the surrounding environment. Instead, their temperatures depended almost entirely on direct exposure to sunlight. In sunlight, they could become extremely hot. In shadow, they could become extremely cold. There was no buffering, no gradual transition, no medium to smooth out the differences. This was not how heat behaved on Earth, and it forced scientists to confront a difficult question. If heat requires a medium to spread, then what happens in the absence of that medium? The answer was both simple and unsettling. Heat as we experience it does not spread at all, not in empty space, because what we call heat is not just energy. It is energy in motion within matter. Without matter, there is no motion to sustain, no collisions to transfer energy, no mechanism to distribute warmth. This realization marked a turning point. It meant that many of our intuitions about heat were not universal truths. They were local experiences, conditions specific to Earth, conditions shaped by an atmosphere that surrounds us at all times. In space, those conditions vanish, and with them the familiar behavior of heat. But even as this new understanding emerged, it created new puzzles. Because if heat cannot spread through empty space, then how does the sun's energy reach Earth at all? How does radiation travel across the vacuum? And more importantly, how does it become heat when it arrives? These questions led scientists deeper into the nature of energy itself. They began to study radiation not just as a carrier of heat, but as a fundamental form of energy transfer. Electromagnetic waves traveling at the speed of light, carrying energy across vast distances without needing a medium. This was a different kind of process, one that did not rely on particles colliding in space, one that could move through emptiness. But it came with a limitation. Radiation does not become heat until it interacts with matter, until it is absorbed, until its energy is transferred into motion. This distinction is subtle but critical, because it means that the space between the sun and Earth is not being heated by the sun. It is being crossed by energy. Energy that only becomes heat when it reaches something capable of absorbing it, like the surface of a planet or your skin. This idea reshapes the entire picture. It separates the journey of energy from the experience of heat. It reveals that what feels like a continuous warming effect is actually a series of interactions happening at specific points, not a property of space itself, but a property of matter within seats. And once you see it that way, the old assumptions begin to fall apart. Heat does not fill the universe. It appears only where conditions allow it, which raises an even deeper question. If heat depends on interaction, then what determines how much energy is absorbed? Why do some objects become hot while others remain cold? Why does Earth maintain a relatively stable temperature while the moon swings between extremes? Because the answer lies not just in the presence of matter, but in how that matter behaves, how it absorbs, how it reflects, how it stores energy. And that is where the story begins to shift from space itself to the objects within it. Because not all matter responds to the sun in the same way. And understanding that difference is the key to unlocking the next layer of this mystery. At first, the contradiction seemed small, a subtle mismatch between expectation and observation. But as scientists gathered more data, it became impossible to ignore. Because the problem was not just that space stayed cold. The problem was that everything about heat as we understood it began to break down when removed from Earth. The deeper we looked, the more inconsistencies appeared. Take the moon, for example. It orbits at nearly the same distance from the sun as Earth. It receives almost the same amount of solar radiation, and yet its surface behaves in a way that feels extreme. During lunar day, temperatures can reach around 120 degrees Celsius. During lunar night, they can drop to minus 170 degrees Celsius. That is a swing of nearly 300 degrees. On Earth, nothing like that happens. Even deserts, which will experience dramatic temperature changes, cannot approach that level of variation. The reason is simple. Earth has an atmosphere. It traps heat, distributes it, and prevents such extremes. But the moon has no atmosphere, no air to carry heat. No medium to smooth out the transition between day and night. And this reveals something critical. The sun does not create a stable temperature. It only delivers energy. What happens to that energy depends entirely on what it encounters. On the moon, sunlight strikes the surface directly. The ground absorbs energy, heats up rapidly, and radiates that energy back into space. But when the sun sets, there is nothing to hold that heat in place. It escapes almost immediately. There is no storage, no buffering, just direct exposure and rapid loss. This pattern repeats across the solar system. Mercury, even closer to the sun, experiences even more extreme conditions. Its day side can reach temperatures of about 430 degrees Celsius, while its night side drops below minus 180 degrees. Again, the same story. No atmosphere, no medium, no way to retain heat. According to scientists studying planetary climates, including teams working with data from NASA and ESA, this presence or absence of an atmosphere is one of the most important factors in determining how a planet responds to solar energy. But even this does not fully resolve the problem, because if radiation is constantly streaming through space, then why does space itself not accumulate that energy over time? Why does it not gradually warm even slightly? This is where the contradiction becomes deeper. Because energy is not being lost, it is being transported. Radiation from the sun travels outward in all directions. Some of it is absorbed by planets, some of it is reflected. Much of it continues outward into deep space. Eventually it encounters other objects, other particles, other regions of matter. But in the vast emptiness between these interactions, it does not build up. It does not linger. It does not behave like heat in a room. Instead, it moves constantly, relentlessly. And this movement is key, because temperature is not just about how much energy exists in a region. It is about how that energy is distributed among particles. In space, there are almost no particles. So even though energy is passing through, there is nothing to distribute it across, nothing to convert that flow into a measurable temperature. This leads to a strange conclusion. Space is not cold because it lacks energy. It is cold because it lacks matter. This idea challenges intuition in a fundamental way. On Earth, we associate warmth with energy. More energy means higher temperature. Less energy means lower temperature. But in space, that relationship breaks down. You can have enormous amounts of energy passing through a region without raising its temperature, because temperature is not a measure of energy alone. It is a measure of energy per particle. And if there are almost no particles, then the temperature remains low no matter how much energy is present. This is why the sun cannot heat space in the way we expect. It can send energy through space, but it cannot create heat without something to absorb that energy. And this brings us to one of the most important distinctions in physics: the difference between energy and heat. Energy is a fundamental quantity. It can exist in many forms. It can move, transform, and be transferred. Heat, on the other hand, is a process. It is the transfer of energy between systems. It's not something that exists independently. It requires interaction. This distinction may seem abstract, but it has real consequences, because it explains why two regions of space, both filled with radiation, can have completely different temperatures. If one region contains more particles, more matter, more opportunities for interaction, then it can have a higher temperature. If another region is almost empty, then even intense radiation will not raise its temperature significantly. This is not just a theoretical idea. It is supported by observations across the universe. Interstellar space. The vast regions between stars is filled with radiation from countless sources. Stars, galaxies, cosmic events all contribute energy. And yet the temperature of this space remains extremely low. According to the measurements of the cosmic microwave background, the baseline temperature of the universe is just 2.7 Kelvin. This is the remnant heat from the Big Bang itself, a faint glow that fills the universe. And even that, after billions of years, has not raised the temperature of space significantly, because once again the same rule applies. Without sufficient matter, energy cannot accumulate as heat. It cannot be stored. It cannot be shared. It simply passes through. This realization forces us to rethink what it means for something to be heated. It's not enough for energy to be present. It must be absorbed. It must be converted. It must become motion within matter. And that process is far more selective than we once believed. Not all surfaces absorb energy equally. Not all materials respond in the same way. Some reflect most of the incoming radiation. Some absorb it and convert it into heat. Some re-emit it quickly. Others retain it. These differences create the diversity of environments we see across the solar system. They determine whether a planet becomes a frozen wasteland or a habitable world. They determine whether sunlight becomes warmth or remains just energy passing through. And yet, even with this understanding, something still feels incomplete. Because if the rules are so clear, then why do certain regions of space behave in ways that seem to defy them? Why are there areas where temperatures appear higher than expected? Why do certain plasmas reach extreme temperatures despite low density? Why does the sun's corona itself reach millions of degrees while the surface below it is cooler? These are not small questions. They are some of the biggest mysteries in astronomy, in astrophysics. And they suggest that while we have begun to understand why space remains cold, there are still deeper layers to uncover, because the story is not just about emptiness. It is about complexity, about interactions we do not fully understand, and about discoveries that are only just beginning to emerge. The mystery might have remained theoretical if we had never gone there. For centuries, everything we understood about heat was built from observation on Earth. Even the most advanced theories were still grounded in environments filled with air matter and constant interaction. But once humanity began sending machines into space, those assumptions were no longer enough, because space does not behave like Earth, and the only way to truly understand it was to go directly into it. This is where modern space missions changed everything. One of the most important breakthroughs came from a mission designed to do something that once seemed impossible. To fly directly into the sun's outer atmosphere, not observe it from a distance, not infer its behavior, but actually pass through it. The mission was the Parker Solar Probe launched by NASA in 2018. Its goal was simple in concept, but extraordinary in execution. Get closer to the sun than any spacecraft in history, close enough to pass through the corona itself, close enough to measure the environment directly. And what it found would challenge everything. Because according to long-standing models, the sun's corona is an extreme environment. Temperatures in this region can exceed 1 million degrees Celsius. That is hundreds of times hotter than the visible surface of the sun. So if a spacecraft were to enter this region, the expectation was clear. It should be destroyed, instantly overwhelmed by heat, reduced to nothing. But that is not what happened. Instead, the Parker Solar Probe survived. Not just briefly, but repeatedly passing through the corona multiple times as it spiraled closer to the sun. And this created a paradox, because the instruments on board confirmed that the corona is indeed extremely hot. According to NASA measurements show plasma temperatures reaching millions of degrees, and yet the spacecraft itself did not experience those temperatures in the way we would expect. Its heat shield, made from advanced carbon composite materials, faced the sun and absorbed the incoming radiation. On the sun-facing side, temperatures could reach around 1,300 degrees Celsius. But just behind that shield, the spacecraft's instruments remained at much lower temperatures close to room temperature. This was not just engineering success, it was scientific evidence. Evidence that being in a high-temperature environment does not necessarily mean you will experience that heat. Because once again, the key factor is interaction. The corona may have particles moving at extremely high speeds, which is why its temperature is so high. But the density of those particles is incredibly low. There are not enough of them to transfer significant energy to the spacecraft. So even though each particle carries a large amount of energy, the total number of interactions remains small. And without frequent interactions, heat transfer remains limited. This is the same principle we have been building toward. Temperature does not equal heat transfer. Energy does not equal warmth. And the Parker Solar Probe provided direct real-world confirmation of this idea. But it was not the only mission to reveal this. Earlier missions such as SOHO, a joint project between NASA and ESA, had already begun to study the sun's outer atmosphere in detail. They observed the corona measured solar wind and detected structures that hinted at complex energy processes. Later missions like Solar Orbiter provided even more detailed observations capturing images and data that showed how energy moves through the sun's atmosphere. Together, these missions painted a picture that was both fascinating and confusing. The sun is constantly releasing energy. The corona is incredibly hot, and yet the space surrounding the sun remains cold, even in regions where energy levels are extremely high. This contradiction forced scientists to ask a deeper question. What exactly is happening in the corona? Why is it so hot? And why does that heat not spread outward into space? Because the corona itself presents a mystery. It's hotter than the surface of the sun. This is known as the coronal heating problem, one of the most enduring questions in solar physics. According to studies published in journals like the Astrophysical Journal, scientists have proposed several explanations. Magnetic reconnection, where magnetic field lines snap and reconnect, releasing energy. Wave heating, where energy travels along magnetic fields and dissipates into the plasma. These processes can explain how energy is added to the corona, but they do not change the fundamental rule. That energy remains within the particles. It does not automatically become heat in the surrounding vacuum. So even as the corona reaches extreme temperatures, the space beyond it remains largely unaffected. Because once the energy leaves the particles and becomes radiation, it spreads out. It disperses. It moves away without accumulating. This is why the Parker Solar Probe can travel through such an environment. It's not immersed in heat in the way we imagine. It's moving through a sparse collection of extremely energetic particles, a region where temperature is high but heat transfer is low. And this distinction is crucial because it shows that our intuition about heat built from dense environments like Earth does not apply in the same way in space. In space, density matters more than temperature. Interaction matters more than energy. And this leads to a new way of thinking about the universe. Instead of asking how hot something is, we begin to ask how much matter is present, how often particles collide, how efficiently energy is transferred, because those are the factors that determine whether something feels hot or remains cold. The Parker Solar Probe did not just survive the sun's corona. It revealed a deeper truth, that the sun cannot heat space in the way we once imagined. It can flood space with energy. But without matter, that energy does not become heat. And this realization opens the door to even more surprising questions. Because if extreme temperatures can exist without significant heat transfer, then what does temperature really mean in the context of space? How should we interpret measurements of millions of degrees? What do they tell us and what do they hide? Because the more we learn, the more it becomes clear. We are not just redefining heat. We are redefining temperature itself. The data came back, and for a moment it seemed impossible. According to instruments aboard the Parker Solar Probe, the region it passed through was measured at temperatures exceeding 1 million degrees Celsius. That number alone should have meant destruction, and yet the spacecraft continued to function. Its systems remained intact. Its instruments kept transmitting. Nothing about that should have been possible if temperature behaved the way we instinctively believe it does. This was the first real shock, because for the first time scientists were not just theorizing about the sun's outer atmosphere, they were inside it, measuring it directly, experiencing its conditions through real hardware, and the results forced a re-evaluation of something deeply fundamental. Temperature does not mean what we think it means. On Earth, temperature and heat feel inseparable. A high temperature means something is hot, something that can burn you, melt objects, transfer energy quickly. The connection feels absolute. But in space, that connection breaks. Inside, the corona particles move at incredible speeds. This is what defines the temperature. According to plasma physics, temperature is proportional to the average kinetic energy of particles. The faster they move, the higher the temperature. So when scientists say the corona is millions of degrees hot, they are describing the motion of individual particles, not the experience of heat, because experience depends on interaction, and here interaction is rare. The corona is incredibly thin, its density is far lower than even the best vacuum we can create on Earth. There are simply not enough particles to collide with a spacecraft frequently enough to transfer large amounts of energy. So even though each particle carries a lot of energy, the total number of collisions remains small. And without collisions, there is no efficient heat transfer. This is where intuition fails, because we are used to environments where particles are everywhere. Air surrounds us. Water surrounds us. Even solid objects are packed with atoms vibrating and interacting. In those environments, high temperature quickly becomes noticeable heat. But remove the density and the relationship changes. You can have extremely fast-moving particles, but if there are very few of them, they cannot deliver much energy overall. It's like being hit by a few very fast-moving grains of sand instead of being immersed in a dense fluid. Each grain carries energy, but the total impact is limited. This is what the Parker Solar Probe experienced. It was not immersed in a dense, blazing inferno. It was moving through a sparse environment where individual particles were energetic, but interactions were infrequent. And that difference is everything, because it reveals that temperature alone is not enough to determine how something behaves thermally. You need to know density. You need to know how many particles are present. You need to know how often they collide. Without that context, temperature can be misleading. And this is not just a detail, it's a fundamental shift in understanding. Because it means that two regions of space can have the same temperature but feel completely different in terms of heat. One could be dense and transfer energy rapidly. The other could be sparse and transfer almost none. The Parker Solar Probe gave scientists a way to see this distinction in action, to measure it directly, and to confirm that the sun's corona is not hot in the way we instinctively imagine. It is hot in terms of particle motion, but not in terms of heat transfer. This realization also helps explain something else that once seemed strange. Why spacecraft need heat shields even in space. Because while the surrounding plasma may not transfer much heat through particle collisions, the radiation from the sun is still intense. Photons carry energy directly. They do not need a medium. They can strike a surface and transfer energy instantly. This is what heats the spacecraft. Not the surrounding particles, but the incoming radiation. The heat shield on the Parker Solar Probe is designed to reflect and absorb this radiation, preventing it from reaching the instruments behind it. So even in a region where the temperature is extremely high, the main source of heat for the spacecraft is radiation, not the environment itself. This distinction is subtle but critical, because it shows that there are different ways energy can be transferred, and not all of them behave the same way. Radiation can travel through empty space. Conduction and convection cannot. So in space, radiation becomes the dominant mechanism. But even radiation has limits. It does not heat space itself. It only heats objects that absorb it. And this is why space remains cold, because there are very few objects to absorb that energy. Most of it simply continues outward, spreading thinner and thinner as it travels, never accumulating, never building up into warmth. This idea becomes even more striking when you consider how energy spreads from the sun. As radiation moves away from the sun, it spreads over a larger and larger area. The intensity decreases with distance. This is known as the inverse square law. So even though the total energy remains enormous, it becomes more diluted as it travels. By the time it reaches Earth, it is still strong enough to warm the planet. But beyond that, it continues to weaken. And beyond the outer planets, it becomes faint. Eventually it merges into the background radiation of the universe, never heating space itself, only interacting where matter exists. This realization changes how we interpret measurements from space missions. When scientists report temperatures of millions of degrees, they are not describing an environment that would instantly destroy anything within it. They are describing the behavior of particles, and that behavior does not automatically translate into heat transfer. This is why the first shock from the Parker Solar Probe was so profound. It showed that our intuition built from life on Earth does not apply universally. It showed that temperature and heat are not the same thing, and it revealed that the sun's ability to heat space is far more limited than we once believed. But this creates a new problem. Because if temperature can be so misleading, then how do scientists make sense of the data they collect? How do they interpret environments where traditional concepts break down? How do they distinguish between energy, temperature, and heat in a way that reflects reality? These questions lead to a period of confusion, a time when even experts had to rethink their assumptions. Because understanding the sun is not just about measuring it, it is about redefining the concepts we use to describe it. And that is where the story becomes even more complex. At this point, something uncomfortable begins to settle in. The data is clear, the observations are consistent, and yet the conclusions feel wrong. Because if temperature can reach millions of degrees without producing intense heat, then what exactly are scientists measuring? What does a number like 1 million degrees actually represent? This question led to a period of real confusion within the scientific community. Not because the physics was incorrect, but because the language we used to describe it was becoming misleading. Temperature, as defined in physics, is a measure of the average kinetic energy of particles. That definition is precise. It is measurable, it is consistent across systems. But the way we interpret that number depends on context. On Earth, high temperature almost always means high heat transfer. That connection is so strong that we rarely separate the two concepts. But in space, that connection breaks. And when it breaks, it creates a gap between what is measured and what is experienced. Scientists working with data from missions like the Parker Solar Probe and earlier observations from Hubble Space Telescope began to realize that they needed to be more careful, because reporting a temperature without context could be misleading. A plasma at 1 million degrees in space is not the same as a gas at 1 million degrees on Earth. The numbers are similar, but the environments are completely different, and that difference changes everything. This confusion became especially important when studying the Sun's corona. According to observations, the corona is much hotter than the Sun's surface. That alone is puzzling. It suggests that energy is being added somewhere above the surface. But when scientists tried to interpret what that temperature meant in practical terms, they encountered a problem. If the corona is so hot, why does it not radiate heat in a way that warms the surrounding space? Why does that energy not spread outward and raise the temperature of the solar system? The answer once again comes back to density and interaction. But explaining that answer in a way that aligns with intuition is not easy, because it requires separating ideas that we are used to combining. Energy and heat, temperature and experience, measurement and meaning. This led to competing interpretations. Some researchers focused on the energy content of the plasma. They emphasized that the corona contains enormous amounts of energy, even if that energy is not easily transferred. Others focused on the low density, arguing that the environment behaves more like a vacuum than a traditional high-temperature system. Both perspectives were correct, but they highlighted different aspects of the same phenomenon. And this created a kind of conceptual tension, a sense that something was missing. Because while the physics could be described mathematically, the intuitive understanding was still incomplete. This is where confusion often arises in science. Not from incorrect data, but from incomplete mental models. The equations work. The measurements are accurate. But the way we think about the system does not fully match reality. In the case of space, the problem is that our intuition is built on environments that are dense and interactive. We expect heat to spread. We expect warmth to fill space. We expect temperature to correspond directly to experience. But none of those expectations hold in a vacuum, and this disconnect becomes even more apparent when we look beyond the Sun. Consider interstellar space. Regions between stars can contain gas at temperatures of thousands or even millions of degrees, yet these regions remain effectively cold in terms of heat transfer. A spacecraft passing through such a region would not experience extreme heating, because once again the density is too low. There are not enough particles to transfer energy efficiently. This pattern repeats across the universe. High temperatures without corresponding heat, energy without warmth, motion without interaction. And it forces scientists to rethink how they communicate these ideas, because words like hot and cold carry everyday meanings that do not always apply in astrophysical contexts. When scientists say a region of space is hot, they are often referring to particle motion, not the sensation of heat. When they say space is cold, they are referring to the lack of interaction, not the absence of energy. This distinction is subtle, but it is essential. Without it, the data can seem contradictory. With it, the picture begins to make sense. But even as this understanding developed, new questions emerged. Because if temperature can be so misleading, then how should we describe environments in space? What metrics should we use? How do we communicate the difference between energy content and heat transfer in a way that is both accurate and intuitive? These questions are still being explored, and they are not just academic. They affect how we design spacecraft, how we protect instruments, how we interpret observations from distant regions of the universe. Because if we misunderstand temperature, we risk misunderstanding the environments we are studying, and that can lead to incorrect conclusions. The confusion surrounding the Sun's corona is a perfect example. For years, scientists struggled to explain why it was so hot. Various theories were proposed: magnetic reconnection, wave heating, turbulent processes. Each offered part of the answer, but none fully resolved the deeper issue. Not just why the corona is hot, but what that heat actually means. Because even if we explain how the energy gets there, we still need to understand how it behaves, how it interacts, how it spreads or does not spread. And this brings us back to the central mystery. The Sun is pouring energy into space. The corona is incredibly hot, and yet space remains cold. At first glance, this seems like a contradiction, but as we have seen, it is not. It is a consequence of how energy and matter interact, or more precisely, how they fail to interact in empty space. Still, there is one more layer to uncover, because understanding that heat requires matter is only part of the story. We also need to understand how radiation interacts with that matter, how energy is absorbed, how it is converted, how it becomes the warmth we experience, because without that step, the puzzle remains incomplete. And that step turns out to be far more subtle than anyone expected. As the confusion deepened, scientists began to approach the problem from different angles. If temperature alone could not explain what was happening, then perhaps the answer lay in how energy actually moves through space. Not just how it exists, not just how it is measured, but how it travels, and more importantly, how it interacts. This is where competing theories began to emerge. Not theories about whether space is cold, that part was no longer in doubt, but theories about why the sun's immense energy fails to turn that surrounding space into a warm environment. At the center of this debate was a simple but powerful idea. Radiation is not the same as heat. It can carry energy, but it does not become heat until it is absorbed. Some physicists focused on this distinction. They argued that the sun is not heating space at all. It is only sending out electromagnetic radiation. This radiation passes through the vacuum without raising its temperature because there is nothing there to absorb it. In this view, space is not resisting heat. It is simply not interacting with it. According to this perspective, the coldness of space is not a mystery. It is the natural result of low density. With almost no particles present, there is nothing to convert radiation into thermal motion. But not everyone was satisfied with this explanation, because it seemed too simple, too clean, and it did not fully address some of the strange observations coming from the sun's outer layers. Other scientists looked more closely at plasma behavior. The corona is not a perfect vacuum. It contains charged particles, magnetic fields, and complex structures. These elements can store and transfer energy in ways that are not immediately obvious. This led to another line of thinking. Maybe the issue is not just about density. Maybe it is about how energy is distributed within the plasma. In this view, the corona is a highly dynamic system. Magnetic fields twist and snap, releasing bursts of energy. Waves travel along field lines, transferring energy from one region to another. Particles are accelerated to high speeds through processes that are still not fully understood. These mechanisms can create extremely high temperatures locally, but they do not necessarily spread that energy outward, because the energy remains tied to the particles and fields within the plasma. Once it leaves that environment as radiation, it disperses. So even in this more complex model, the same conclusion begins to emerge. Energy can be concentrated, it can be stored, it can be released in bursts, but without sufficient matter, it cannot be shared as heat. Another theory focused on the concept of radiative equilibrium. According to this idea, objects in space reach a balance between the energy they absorb and the energy they emit. A planet, for example, absorbs sunlight and re-emits energy as infrared radiation. Over time, it settles into a stable temperature. But space itself does not have a surface. It does not absorb and re-emit energy in the same way, so it cannot reach an equilibrium temperature. It remains, in a sense, invisible to radiation, unaffected by it. This perspective helped explain why planets can be warm while the space around them remains cold. Because planets have matter. They have surfaces. They have atmospheres that can absorb, store, and redistribute energy. Space has none of these, so it cannot participate in the same process. There was also discussion about particle density thresholds. Some scientists propose that there is a minimum density required for radiation to effectively convert into heat. Below that threshold, energy simply passes through without significant interaction. Above it, interactions become frequent enough to sustain a measurable temperature. This idea aligned with observations from different regions of space. Dense interstellar clouds can have temperatures that reflect their energy content. Diffuse regions remain cold even when exposed to radiation. Again, the same pattern. Density determines interaction. Interaction determines heat. But perhaps the most intriguing line of thought came from those studying the nature of temperature itself. Because if temperature can exist without meaningful heat transfer, then maybe temperature is not the best way to describe these environments. Maybe we need a different framework. Some researchers suggested focusing on energy density instead, how much energy exists in a given volume. Others looked at particle flux, how many particles are moving through a region over time. Others still examined radiative intensity, the flow of energy through space. Each of these metrics captures a different aspect of the system, and together they provide a more complete picture, because no single number can fully describe what is happening. Temperature alone is not enough. Energy alone is not enough. Interaction alone is not enough. It is the combination of all three that determines how an environment behaves. This realization marked a shift in how scientists approach the problem. Instead of searching for a single explanation, they began to build a layered understanding, one that separates different processes, one that recognizes that what we call heat is not a single phenomenon. It is the result of multiple factors working together, and sometimes is not working together at all. In the case of space, those factors are mostly absent. There is energy, there is radiation, there are particles, but there is very little interaction. And without interaction, heat does not emerge, even if the ingredients are present. This is the key insight that began to unify the competing theories. They were not contradicting each other. They were describing different parts of the same system. Radiation carries energy. Plasma can store and release it. Magnetic fields can redistribute it. But none of these processes on their own can create heat in empty space. They require matter. They require density. They require interaction. Without those, the universe remains cold, even in the presence of immense energy. And yet, even as this understanding began to take shape, something still remained unresolved. Because while these theories explained why space does not heat up, they also raised a deeper question. If heat only emerges through interaction, then what exactly happens at the moment of interaction? How does radiation, which travels silently through empty space, suddenly become warmth when it strikes matter? What is the mechanism that transforms invisible energy into something you can feel? Because that transformation is where everything changes. The breakthrough did not come from a single moment. It emerged slowly as the different pieces of the puzzle began to align. Observations from missions like the Parker, solar probe data from telescopes like the Hubble Space Telescope, and decades of theoretical work all pointed toward the same conclusion. The problem was never the sun. The problem was our definition of heat. For a long time, heat was treated as something that could exist independently, something that could fill a space, accumulate, and spread outward from a source. But as scientists examined the behavior of energy in space, that idea began to collapse. Heat is not a thing. It is a process. Specifically, it is the transfer of energy between systems, and that transfer requires interaction. This realization seems simple in hindsight, but it has profound consequences, because it means that energy can exist without heat. Energy can move through space, travel vast distances, and never become heat unless it interacts with matter. This is the breakthrough. It separates two ideas that we instinctively combine. Energy and heat are not the same. Energy is fundamental. Heat is conditional, and once you understand this, the paradox of the sun begins to dissolve. The sun is constantly releasing energy in the form of electromagnetic radiation. According to NASA, this energy spans a wide range of wavelengths from visible light to ultraviolet and infrared. These photons travel through space at the speed of light. They do not need a medium. They do not slow down. They do not lose energy in the way that moving objects on Earth do. They simply move, and as they move, they spread out. Their intensity decreases with distance, but the energy itself remains. Until they encounter something, that encounter is the key. Because when a photon strikes a surface, it can do one of several things. It can be reflected, it can be transmitted, or it can be absorbed. If it is absorbed, its energy is transferred to the atoms and molecules of the material. Those atoms begin to vibrate more rapidly. Their motion increases, and that increase in motion is what we perceive as heat. This is the moment where energy becomes heat. Not before, not during its journey through space. Only at the point of interaction. This explains something that once seemed contradictory. Why sunlight feels warm on your skin even though the space it traveled through is cold. The warmth is not in the sunlight itself. It is in your skin. in the molecules that absorb the energy and begin to move. This is why different materials heat up differently in sunlight. Dark surfaces absorb more radiation and convert more energy into heat. Light surfaces reflect more radiation and remain cooler. This is not because the sunlight changes, it is because the interaction changes. The same principle applies on a larger scale. Planets absorb solar radiation and convert it into heat. Some of that heat is retained, some is re-emitted into space. Over time, a balance is reached. This balance determines the planet's temperature. According to studies from institutions like MIT and Harvard University, this process is influenced by many factors. Atmospheric composition, surface properties, and energy distribution all play a role. But the underlying mechanism remains the same. Radiation arrives, matter absorbs it, motion increases, heat emerges. Without that sequence, heat does not exist, and this is why space remains cold. Because in the vast emptiness between objects, that sequence rarely occurs. Photons pass through, particles are too sparse, interactions are too infrequent, so the energy never becomes heat, it remains energy. This also explains why the concept of temperature becomes so complex in space. When scientists measure the temperature of a plasma, they are measuring the motion of particles. But that motion does not necessarily translate into heat transfer, because heat transfer depends on collisions, and collisions depend on density. So you can have a plasma with extremely high temperature but very low heat transfer. This is exactly what we see in the sun's corona. Particles are moving rapidly, temperatures are high, but density is low. So interactions are limited, and heat transfer is minimal. This is the breakthrough that unifies everything. It explains the coldness of space. It explains the behavior of the corona. It explains why spacecraft can survive in environments that seem impossibly hot. And it explains why sunlight can warm a planet without warming the space around it. Because heat is not carried through space. It is created at the point of interaction. This idea also reshapes how we think about energy in the universe. Energy is everywhere. Stars, galaxies, and cosmic events constantly release it. But heat as we experience it is rare. It only exists where matter is present, where interaction can occur, where energy can be converted into motion. And this leads to a deeper realization. The universe is not filled with warmth. It is filled with energy. Cold, silent energy moving through vast emptiness, occasionally interacting, occasionally becoming heat, but mostly passing through. This perspective changes how we see the cosmos. It is not a place where heat spreads freely. It is a place where heat must be created, again and again, at every point where energy meets matter. And this raises an even more intriguing question. If heat depends on interaction, then what happens in environments where interaction is more complex, where matter is dense, where energy is trapped, where feedback loops amplify the effects? Because not all systems are as simple as empty space. Some environments behave in ways that seem to amplify heat beyond what we would expect, and understanding those environments reveals just how powerful this mechanism can be. To truly understand this, you have to let go of something familiar. You have to stop thinking of heat as something that exists out there in space, and start thinking of it as something that only comes alive at the moment of contact. A simple analogy makes this clearer. Imagine standing in the rain. Not a gentle drizzle, but a steady stream of droplets falling from above. Each drop carries energy. Each drop can transfer that energy when it hits you. Now imagine two very different scenarios. In the first, the rain is dense. Countless droplets strike your skin every second. The impact is constant. The energy transfer is continuous. You feel soaked, overwhelmed by the accumulation of tiny impacts. In the second, the rain is almost non-existent. Only a few droplets fall spaced far apart. Each one still carries energy, still it's with the same intensity, but the overall effect is minimal. You barely feel it. This is the difference between heat in a dense environment and energy in space. In both cases, the individual units carry energy, but the experience depends on how many interactions occur. Now take that idea and replace the raindrops with photons. Sunlight is a stream of energy traveling across space. When it reaches the surface, it delivers that energy, but the effect depends entirely on how that surface interacts with it. If the surface absorbs the photons efficiently, the energy is converted into motion. Molecules begin to vibrate, temperature rises, heat is felt. If the surface reflects most of the photons, very little energy is absorbed. The temperature remains low. The same sunlight, completely different outcomes. This is why wearing dark clothing in sunlight makes you feel warmer. Dark materials absorb more radiation. Light materials reflect it. It is not the sun changing, it is the interaction. And this interaction becomes even more important when we scale up. Consider the difference between the Earth and the Moon. Both receive sunlight. Both are exposed to the same source of energy, but their responses are dramatically different. Earth has an atmosphere. That atmosphere does more than just contain air. It acts as a system for capturing, redistributing, and retaining energy. When sunlight reaches Earth, some of it is reflected back into space. Some of it is absorbed by the surface. That absorbed energy is then re-emitted as infrared radiation. But the atmosphere traps part of that outgoing radiation. It absorbs it, re-emits it, and sends some of it back toward the surface. This creates a feedback loop. Energy enters, it is absorbed, it's partially trapped, and over time this leads to a stable temperature. This is known as the greenhouse effect, and it is essential for maintaining conditions suitable for life. Without it, Earth would be far colder, closer to the baseline temperature of Space. The Moon, on the other hand, has no atmosphere. When sunlight strikes its surface, the energy is absorbed and then quickly re-emitted. There is no system to retain that energy, no mechanism to distribute it. So temperatures rise quickly in sunlight and fall just as quickly in darkness. The difference between Earth and the Moon is not the sun. It is the interaction, the presence of matter, the ability to absorb, store, and redistribute energy. This same principle applies across the universe. Gas giants like Jupiter have thick atmospheres that trap heat. Small asteroids with little mass and no atmosphere cannot retain energy and experience extreme temperature swings. Even within a single object, different materials can respond differently to the same radiation. This is why some surfaces heat up faster than others. Why some regions retain warmth while others cool rapidly. Because heat is not delivered by the sun in a uniform way. It is created locally, at the point where energy meets matter. This idea also helps explain something that might seem counterintuitive. Why space itself does not warm up over time. Because for space to warm, it would need to absorb energy. It would need to convert that energy into motion. But space, by definition, contains almost no matter. So there is nothing to absorb the energy, nothing to convert it, nothing to retain it. This energy passes through, but it does not stay. It does not accumulate. It does not build into heat. This is why the universe remains cold even though it is filled with radiation. Because radiation alone is not enough. You need interaction. You need matter. You need a system that can capture and transform energy. And this brings us back to the sun. The sun is not heating space. It's providing the raw material for heat, energy. That energy travels outward, waiting to be absorbed, waiting to be transformed. And where it is absorbed, heat appears. Where it is not cold, remains. This distinction may seem subtle, but it changes how you see everything. Because it means that warmth is not something that exists independently. It is something that must be created, again and again, at every surface, at every particle, at every moment of interaction. And once you see that the universe begins to feel very different, not like a place filled with warmth spreading outward from stars, but like a vast cold backdrop punctuated by isolated pockets of heat, places where energy and matter meet, places where motion emerges, places where warmth briefly exists, before fading again into the cold. But this raises an even more profound question. If heat only exists where energy is absorbed, then how does this shape the behavior of entire systems? How does it influence the structure of planets, the evolution of atmospheres, the formation of stars? Because once you understand how heat is created, you begin to realize how much of the universe depends on it. Once you begin to see heat as something that only exists through interaction, a pattern starts to appear across the entire universe. A pattern that connects planets, stars, and even the vast emptiness between galaxies. Because the same principle repeats everywhere. Energy moves freely, heat does not, and this simple distinction reshapes how we understand nearly every system in space. Start with planets. Each planet in the solar system receives energy from the sun, but the way that energy is handled varies dramatically. Take Venus. It is only slightly closer to the Sun than Earth, receiving about twice as much solar radiation. But its surface temperature is not just higher, it is extreme. Around 460 degrees Celsius, hot enough to melt lead. This is not because the Sun is heating Venus more effectively through space. It is because Venus traps that energy. Its thick atmosphere, composed largely of carbon dioxide, creates a powerful greenhouse effect. Incoming radiation is absorbed by the surface, re-emitted as infrared, and then trapped by the atmosphere. Energy enters, but it cannot escape easily, so it accumulates. And as it accumulates, the motion of particles increases. Temperature rises, heat intensifies. Now compare that to Mars. Mars also receives sunlight, but its atmosphere is thin. It cannot trap energy effectively, so even though it absorbs some radiation, much of that energy is quickly lost. Temperatures remain low. The planet is cold. The difference is not the Sun. It is the interaction, the ability to capture and retain energy. This pattern continues as you move further outward. Gas giants like Jupiter have thick atmospheres that can absorb and redistribute energy internally. In fact, Jupiter emits more energy than it receives from the Sun due to internal processes like gravitational compression. Here, heat is not just coming from outside. It is being generated and stored within. Again, the key factor is matter, the presence of dense interacting particles, the ability to convert energy into sustained motion. Even small objects follow the same rule. Asteroids with little mass and no atmosphere cannot retain heat. They heat up quickly when exposed to sunlight and cool down just as quickly when in shadow. They do not store energy. They do not distribute it. They simply respond moment by moment, and this reveals something profound. Heat is not a universal background condition. It is a local phenomenon. It exists only where conditions allow it. This idea extends beyond planets. It applies to entire regions of space. Consider nebulae, vast clouds of gas and dust scattered across the galaxy. Some nebulae are cold with temperatures just a few degrees above absolute zero. Others are much warmer, heated by nearby stars or internal processes. The difference once again comes down to density and interaction. In denser regions, particles collide more frequently. Energy is shared more effectively. Temperature rises. In diffuse regions, particles are sparse, collisions are rare. Even if energy is present, it does not translate into heat. Telescopes like the James Webb Space Telescope have allowed scientists to observe these environments in unprecedented detail. By analyzing infrared radiation, researchers can map how energy is absorbed and emitted across different regions. What they see reinforces the same principle. Where matter is present and interacting, heat emerges. Where it is not, cold persists. This pattern even applies to the larger scales. Galaxies, clusters, and the intergalactic medium all show variations in temperature based on density and interaction. Hot gas can exist in clusters of galaxies heated by gravitational processes and shock waves, but the vast spaces between these structures remain cold. Energy flows through them, but without sufficient matter it does not accumulate. This changes how we think about the universe as a whole. It is not a place where heat spreads outward from stars gradually warming everything. It's a place where energy moves constantly, but heat appears only in specific locations, isolated pockets, planets, stars, dense clouds. Everywhere else, the universe remains cold, and this has important consequences, because it means that the conditions required for warmth are relatively rare. They depend on the right combination of factors: distance from a star, atmospheric composition, material properties, energy balance. Without these, even a planet receiving sunlight can remain cold. This is why the search for habitable worlds is so complex. It is not enough to find a planet at the right distance from its star. You also need the right conditions for energy to be absorbed and retained. The right atmosphere, the right surface, the right interactions. Because without those, the energies from the star will pass by, without creating the warmth needed for life. This insight has guided research at institutions like NASA and ESA, as well as universities such as Caltech. Scientists are not just looking for energy sources, they are looking for environments where that energy can become heat, where interaction can sustain motion, where warmth can persist, because that is what makes a world livable. And this brings us back to the central idea. The sun does not heat space. It provides energy, What happens to the energy depends entirely on what it encounters, and this realization does more than explain why space is cold. It reveals how fragile warmth really is, how dependent it is on specific conditions, how easily it can disappear. Because without interaction, without matter, without the right environment, heat does not exist, even in a universe filled with energy. But this understanding also raises a deeper implication. If heat is so dependent on interaction, then how does this shape the evolution of entire systems over time? How does it influence the formation of stars, the collapse of gas clouds, the balance between radiation and gravity? Because the way energy becomes heat is not just a detail. It's a driving force behind the structure of the universe itself. Once you begin to see heat as something that must be created through interaction, the universe stops looking simple. It starts to look selective, because energy is everywhere, but warmth is not. And that changes how we understand the structure of everything around us. For a long time, scientists imagined stars as the primary sources of heat in the universe. Massive engines of energy radiating outward, shaping the environments around them. This idea is still true in part, but it is incomplete, because stars do not spread heat, they spread energy. And what happens to that energy depends entirely on the systems it encounters. This realization has forced scientists to rethink models of planetary systems, stellar environments, and even the large-scale behavior of galaxies. Take planetary formation, for example. In the early stages of a solar system, a disk of gas and dust surrounds a young star. This protoplanetary disk is filled with particles colliding, interacting, exchanging energy. In these dense regions, energy can accumulate. Collisions generate heat. Friction increases motion. Temperatures rise. This is what allows solid materials to form, melt, and reform. This is what drives the creation of planets. But as you move outward from these dense regions, the disk becomes thinner. Interactions become less frequent. Even though radiation from the star continues to pass through, the ability to convert that energy into heat decreases. So temperature drops. This creates distinct zones within the disk. Hot inner regions where rocky planets form. Colder outer regions where gases and ices dominate. This structure is not just about distance from the star. It is about density, about interaction, about where energy can become heat. This same principle applies to atmospheres. On Earth, the atmosphere acts as a mediator between incoming solar radiation and the surface. It absorbs certain wavelengths, reflects others, and redistributes energy through convection and circulation. This creates a relatively stable climate. But small changes in an atmospheric composition can have large effects. Increase greenhouse gases and more energy is trapped. Reduce them and more energy escapes. According to research published in journals like Nature and studies conducted by organizations like NASA, these feedback mechanisms are critical in determining a planet's long-term temperature. Again, the key is interaction. The more effectively energy is absorbed and retained, the warmer the system becomes. But this also introduces instability, because if too much energy is trapped, temperatures can rise uncontrollably. This is what likely happened on Venus, a runaway greenhouse effect where increasing temperatures caused more greenhouse gases to be released, which in turn trapped more heat. A feedback loop, an amplification of interaction, and it transformed the planet into an extreme environment. On the other end of the spectrum, consider the outer reaches of the solar system. Beyond the orbit of Neptune, sunlight is faint. Radiation still travels outward, but its intensity is low, and the density of matter is also low. So interaction is minimal. These regions remain cold, frozen, not because energy is absent, but because it cannot be converted into heat effectively. This pattern extends even further into interstellar space, into the vast regions between stars. Here the density is so low that interactions are incredibly rare. Even though radiation from countless stars passes through these regions, the temperature remains close to the cosmic baseline, around 2.7 Kelvin. This is not because the universe lacks energy. It's because the universe lacks the conditions needed to turn that energy into heat. This realization has changed how scientists think about cosmic environments. Instead of focusing solely on energy sources, they now consider the pathways through which energy is converted, how it is absorbed, how it is stored, how it is released, because these processes determine the thermal structure of the universe. They shape where heat exists, where it does not, and how systems evolve over time. This also affects how we interpret observations. When telescopes detect radiation from distant objects, they are not directly measuring heat. They are measuring energy. To understand temperature, scientists must consider how that energy interacts with matter, how it is distributed, how it is converted. This adds complexity, but it also adds clarity, because it explains why some regions appear hotter than others, why some environments are stable while others are extreme, why some planets can support life while others cannot. All of it comes back to interaction, to the ability of matter to capture and transform energy, and this leads to a deeper implication. Heat is not just a passive result of energy. It is an active process, a process that depends on the structure of matter, on the behavior of systems, on the balance between absorption and emission. In this sense, heat becomes a kind of signature, a reflection of how a system interacts with energy. And this has profound consequences, because it means that by studying heat, we can learn about the underlying structure of the universe. We can infer the presence of atmospheres. We can detect the composition of distant planets. We can understand the dynamics of stars and galaxies, all by observing how energy is converted into heat. But it also reminds us of something more fundamental. That warmth is not guaranteed. It is not a default condition. It is something that must be created, maintained, sustained through interaction. And without that interaction, even the most powerful sources of energy cannot produce heat. This is the true implication of the sun's inability to heat space. It is not a limitation of the sun. It is a property of the universe, a rule that governs how energy behaves. And once you understand that rule, you begin to see the universe differently, not as a place filled with warmth, but as a place where warmth is rare, where it emerges only under the right conditions, where it exists briefly, locally, and conditionally, and everywhere else. There is cold. But even with this understanding, there are still questions that remain unanswered, because not all observations fit neatly into this framework. There are anomalies, regions where temperatures behave in unexpected ways, phenomena that challenge even these refined models, and those mysteries are still waiting to be solved. Even with everything we now understand, something still does not quite fit. The rules seem clear. Heat requires interaction. Energy must be absorbed to become warmth. Without matter, space remains cold, and yet there are exceptions, or at least there are observations that do not fully align with this clean, elegant picture. One of the most persistent mysteries is still the sun's corona. Despite decades of study, scientists have not fully explained why it reaches temperatures of millions of degrees, while the surface below it remains much cooler. According to research published in journals like the Astrophysical Journal, this coronal heating problem remains one of the biggest unsolved questions in solar physics. We know that energy is somehow being added to the corona. We know that magnetic fields play a role. We know that waves and turbulence may be involved, but we do not yet have a complete unified explanation. And this matters, because it suggests that our understanding of how energy is transferred and converted is still incomplete. There may be processes at work that we do not fully grasp. Processes that could change how we think about heat in extreme environments. Another mystery lies in certain regions of interstellar space. In some cases, gas clouds have been observed at temperatures that seem higher than expected, given their density and energy input. Observations from telescopes like the Hubble Space Telescope and more recently the James Webb Space Telescope have revealed complex structures where energy appears to be concentrated in unexpected ways. These environments are not dense enough to behave like planetary atmospheres, and yet they are not completely cold. Something is allowing energy to be retained or redistributed more effectively than simple models would predict. One possible explanation involves shock waves. When gas clouds collide or when stellar winds interact with surrounding material, shock fronts can form. These fronts compress the gas, increasing density and allowing energy to be converted into heat more efficiently. But even this does not explain everything, because in some cases the observed temperatures still exceed what shock heating alone can account for. There are also questions about how energy moves through magnetic fields. In plasma environments, charged particles follow magnetic field lines. Energy can be transported along these khutut in ways that are not immediately intuitive. Waves can carry energy across large distances and deposit it in specific regions. This could help explain localized heating, but the details are still being worked out. Scientists at institutions like Caltech and MIT continue to study these processes, using both observations and simulations to explore how energy behaves in complex systems. And then there is the question of dark matter. While dark matter does not interact with electromagnetic radiation in the same way as normal matter, it makes up a significant portion of the universe's mass. Its presence influences the formation of galaxies and the movement of matter on large scales. But how it interacts with energy remains unknown. Could it play a role in thermal processes at cosmic scales? Could it affect how energy is distributed in ways we do not yet understand? These questions remain open. There are also anomalies closer to home. In Earth's own upper atmosphere, temperatures can vary in ways that are not always intuitive. The thermosphere, for example, can reach temperatures of over 1000 degrees Celsius. And yet, because the density is so low, an object in this region would not feel hot. This is another example of the same principle. High temperature does not always mean high heat transfer, but it also highlights how complex these systems can be, because even within a single environment, different layers can behave in very different ways. Energy can be added, redistributed, and lost through multiple processes, and not all of them are fully understood. Even the cosmic microwave background, the faint radiation left over from the Big Bang, raises questions. It sets the baseline temperature of the universe. But why has it cooled to exactly this level? How has it evolved over time? And how does it interact with matter in different regions? These are questions that cosmologists continue to explore, because understanding the thermal history of the universe is key to understanding its evolution. All of these mysteries point to the same conclusion. We understand the broad principles. We know that heat requires interaction. We know that space remains cold because it lacks matter, but the details are still being uncovered. There are processes we do not fully understand, interactions we have not yet observed, mechanisms that may operate differently under extreme conditions. And this is what makes science so compelling. Every answer leads to new questions. Every solution reveals new complexities. The more we learn, the more we realize how much remains unknown. And in the case of heat and energy in the universe, those unknowns are still significant. Because while we can explain why the sun cannot heat empty space, we cannot yet explain every way in which energy behaves once it leaves the sun. We cannot fully predict how it will interact with every environment. We cannot account for every anomaly. And that means the story is not finished. Not even close. There is still more to discover, more to understand, more to uncover about the nature of energy, matter, and the delicate balance that creates heat. And the tools we use to explore these questions are becoming more powerful with every passing year. New missions, new telescopes, new technologies, all designed to push the boundaries of what we know. Because somewhere in that data, somewhere in those observations, there may be answers that change our understanding once again. The next answers will not come from theory alone. They will come from machines sent into places we cannot go. Because if the mystery of heat in space has taught us anything, it is this. We cannot rely on intuition. We have to measure. We have to observe. We have to go there. And right now, a new generation of missions is doing exactly that. At the forefront is the James Webb Space Telescope. Unlike earlier telescopes, Webb is designed to observe the universe in infrared light. This is crucial because infrared radiation is directly linked to how objects absorb and emit energy. In other words, it allows scientists to see heat, not as we feel it, but as it actually behaves. With Webb, researchers can study the thermal structure of distant planets, map the energy distribution in nebulae, and observe how radiation interacts with matter across vast distances. Already early observations have revealed details that were previously invisible. Cold regions of space that still emit faint infrared signals, dust clouds that absorb and re-emit energy in complex patterns, exoplanets with atmospheres that trap heat in unexpected ways. Each of these observations adds another piece to the puzzle, another layer to our understanding of how energy becomes heat. But Webb is only one part of the story. Closer to home, missions like the Solar Orbiter continue to study the sun in detail. By observing both the surface and the corona, Solar Orbiter is helping scientists understand how energy moves through the sun's atmosphere. It works alongside the Parker Solar Probe, which continues to dive deeper into the corona, collecting data from regions never explored before. Together, these missions are providing a more complete picture, not just of the sun, but of how energy behaves in extreme environments. They are measuring particle densities, magnetic fields, wave activity, and radiation levels. They are capturing the subtle interactions that turn energy into motion. And with each pass, they bring us closer to answering questions that have remained unresolved for decades. Beyond the Sun, new missions are being planned to study the outer solar system and beyond. The Europa Clipper, for example, will explore the icy moon Europa, investigating how energy from Jupiter's gravitational pull may create subsurface oceans. Here, heat is not coming from sunlight alone. It's being generated internally through tidal forces, another form of interaction, another way energy becomes heat. Similarly, missions targeting Titan, Saturn's largest moon, aim to understand how complex atmospheres interact with solar radiation. Titan's thick, hazy atmosphere traps energy in ways that are still not fully understood. Even in these distant, cold environments, the same principle applies. Where energy is captured and transformed, heat appears. Where it is not, cold remains. And then there are the telescopes of the future. Projects being developed by organizations like NASA and ESA aim to push even further. More sensitive instruments. Higher resolution observations. The ability to detect smaller differences in energy and temperature. These tools will allow scientists to study the universe in ways that were previously impossible, to observe how energy flows through the interstellar medium, to measure how radiation interacts with the smallest particles, to detect subtle variations that could reveal new physics. Because despite everything we have learned, there is still much we do not understand. The coronal heating problem remains unsolved. The behavior of plasma in extreme conditions is still being explored. The role of magnetic fields in energy transfer is not fully understood, and beyond that there may be entirely new mechanisms waiting to be discovered. Processes that operate under conditions we have not yet been able to observe. Processes that could reshape our understanding of heat and energy. This is why these missions matter. They are not just collecting data. They are testing the limits of our understanding. They are challenging our assumptions. They are revealing where our models succeed and where they fail. And perhaps most importantly, they are showing us that the universe is more complex than we imagined, that even something as familiar as heat can behave in ways that defy intuition, that the rules we take for granted are not universal. They are conditional, dependent on environment, dependent on interaction. And this realization changes how we approach science. It reminds us to question assumptions, to look deeper, to separate what we observe from how we interpret it. Because the next discovery may not come from finding something new. It may come from seeing something familiar in a completely different way. And as these missions continue, as new data arrives, as new patterns emerge, we move closer to a deeper understanding, not just of the sun, not just of space, but of the fundamental nature of energy itself, and what it really means for something to be hot. In the end, the answer is not what you expect. The sun does not fail to heat space. It never could, because space was never something that could be heated in the first place. What feels like a contradiction is actually a misunderstanding, not of the sun, but of heat itself. For most of your life, heat has felt like a property of the world around you. Something that fills a room, something that surrounds your body, something that exists in the air. But that experience is local. It is specific to Earth. It is the result of being immersed in matter. Take that away and the illusion disappears. Because heat is not something that exists independently. It is something that happens. A process. A transformation. Energy becomes motion. Motion becomes temperature. And only then does warmth exist. This is the quiet truth that reshapes everything. The universe is not filled with warmth spreading outward from stars. It is filled with energy moving silently through emptiness. Cold, invisible, constant. And only in rare places does that energy become something more. On the surface of a planet, inside the atmosphere of a world, within the dense interior of a star. In these places, matter captures energy, holds it, transforms it, and for a moment heat appears. But outside those places, the universe remains as it truly is. Cold, not because it lacks energy, but because it lacks interaction. This changes how you see the sun. It's no longer a source of heat in the way a fire is. It is a source of energy. a constant stream of photons traveling outward in all directions, waiting to encounter something, waiting to be absorbed, waiting to become heat. And when it does, the effect can be profound. On Earth, that interaction creates the conditions for life. It drives weather, it powers ecosystems, it shapes the entire environment, but it does not warm the space between. That space remains untouched, unaffected, silent. And this silence extends far beyond our solar system, across galaxies, across the vast emptiness between stars. Energy flows endlessly, but heat appears only in scattered pockets, isolated, fragile, dependent on conditions that are not guaranteed. This realization carries a deeper implication. Warmth is not the default state of the universe. It is the exception, a temporary alignment of factors, a balance between energy and matter, and that balance can be easily disrupted. Remove the atmosphere and a planet becomes extreme. Reduce the density and heat disappears. Change the composition and energy is no longer retained. Everything depends on interaction. Everything depends on the ability to convert energy into motion. And without that ability, even the most powerful star cannot create warmth. This is why space feels so different from anything you know. It is not just empty, it is fundamentally different. The rules that shape your everyday experience do not apply. Heat does not spread. Temperature does not behave intuitively. Energy does not accumulate. Instead, everything is defined by absence. The absence of matter, the absence of interaction, the absence of the conditions required for heat to exist. And yet within that absence, something remarkable happens. Because where the right conditions do exist, where matter gathers, where energy is captured, where interaction becomes possible, heat emerges, life becomes possible. Complex systems form. The universe in all its coldness creates pockets of warmth, islands of activity in a vast silent sea, and you are standing on one of them, on a planet that captures just enough energy, that holds it just long enough, that transforms it in just the right way, to create an environment where warmth is stable, where heat is sustained, where life can exist. And that makes your experience of warmth something rare, something special, something that depends on a delicate balance. Because without that balance, without the right conditions, without the constant interaction between energy and matter, the universe would feel very different. It would feel like space, cold, silent, unchanging. So the next time you step into sunlight and you feel that familiar warmth on your skin, remember what is really happening. It is not the sun heating the space around you. It is not warmth traveling across the vacuum. It's energy arriving after a long journey. And in the instant it touches you, it becomes heat.